Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the current mirror. And essentially, in this video, we're going to dive into the problem which the current mirror helps us to solve in our electronics. And secondly, we're going to derive this current mirror equation here, given by I out, which is the current that is being mirrored through this M2 transistor. And the equation says that I out is equated to the width over the length of my M2 transistor divided by the width over the length of my M1 transistor times this I reference. And we'll also dive more into what I reference is relating to. So the two main problems which the current mirror helps us to solve are one, which is it is independent of my temperature, and the second is the current being independent of the power supply voltage. And we can see that in the sense that if we have a transistor, let's just say an NMOS, and we use it as a voltage controlled current source, right? If we attach a battery here, and if this battery is above our threshold voltage, so for example, if we take a silicon based transistor, if my battery is above 0.7 volts, it will generate a current here, call this ID. And essentially this ID, if we ignore channel length modulation, is going to be 1/2 mu n, which is the electron mobility, times the oxide capacitance, times the width over the length of the transistor, times the V battery, minus V threshold squared. And again, the thing that we're ignoring is channel length modulation, which is 1 minus gamma V ds. So we're ignoring this. But as you can see, ID is dependent on this electron mobility, which varies with temperature, and this V battery, which also varies with temperature. And a good way to visualize this battery dying down is if you leave your car in extreme hot temperatures for a long period of time, you might need to jump start it when you come back to use the car after a month or two. So essentially we can say that temperature varies our V battery and this electron mobility. Now, normally in standard electronics, we have a global power supply voltage. Let me call this VDD. And we distribute these voltages to our different components. So in this case, we might build a voltage divider network and take the voltage from this voltage divider and then use our transistor as a voltage controlled current source. And in this situation, we still generate an ID if this voltage here, call this Vin, is greater than VTH. So ID in this case will be, again, 1/2 mu n cox W over L times this Vn is going to be the voltage divider equation. So if I call this R2 and I call this R1, it's going to be R2 over R1 plus R2 times Vn minus VTH squared. Again, we're ignoring channel length modulation. And in this equation, you can better visualize the effect of temperature, because as temperature increases and decreases, these resistor values are going to differ. As a result, this whole power supply voltage is going to vary up and down, and which will change the currents that we're getting. So now as a solution, we create this current mirror as a way to have a stable current ID, which is independent of temperature and power supply voltage. So essentially, this is the reason why we use the current mirror. I hope this makes sense. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. So before we derive the equation of the current mirror, we want to talk about the basic concepts of the current mirror, or how do we go about building it, right? And essentially, the first thing you need for the current mirror is you need to build what's called a golden current source. And this has to be a current source that is stable, power supply voltage, and temperature independent, using what's called a band gap circuit. So this means that before we have a current mirror, we need what's called a band gap circuit. And I'm not going to talk or dive into this band gap circuit because it's a very complex topic, and I'll save that for another video, where basically a band gap circuit is a precision circuit designed to produce a constant output voltage regardless of changes in temperature or power supply. And we can combine this voltage reference with resistors and current mirrors to generate a stable constant current reference. So we call this current reference Iref. And what we want to do now is build this, let's call it a black box for now, because we don't know what's in it. And basically the second step is to copy or clone this current source to build many others, or basically copy it into what's called I out 1 and maybe another current source, call it I out 2, and so on and so forth. And essentially these I outs or mirrored currents are going to be power supply voltage independent and temperature independent. So I hope this makes sense in the direction that we're going. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Now let's go ahead and figure out what is in this black box. So to begin, we want to build a circuit that looks like this. And as you can see, this is what is called a diode connected device. And I've talked about this diode connected device in the video previous to this one, so please feel free to check that out. I've posted a link in the top right hand side corner of this video. And essentially what we want to do is we want to see what happens to ID as we vary VG. And we know that VG in this case is equated to VD for a diode connected MOSFET. Again, because this here is VD and this here is VG, and they're connected by this node here. So basically they're the same. So as we vary VG, ID is going to be 0 all the way until this V threshold. And then it's going to start to shoot up like so. And essentially this is the IV characteristics of a diode connected NMOS transistor. Now for this example, what we want to note is this region here. And this is the region that we call the saturation region. And we call this the saturation region because in the saturation, VDS has to be greater than VGS minus VTH. And this is basically true because VDS is basically VGS because D and G are the same. And that's greater than VGS minus VTH. Another way to see this is that VS, which is connected here, is basically ground. So VG is greater than VG minus VTH, which is true because, again, this VTH is like 0.7. And whatever VG is, it's already on this side. So you take its value and subtract 0.7. So this left-hand side is going to be bigger. So since we're in the saturation region, we can write an equation for ID, and this equation will be 1/2 mu n COX W over L VG minus VTH. Again, let's ignore channel length modulation. And again, note that this is ID in the saturation region. Let's call this equation number 1. Okay, the next step here is to consider that we are varying now our current source. So let's vary an ID and see what happens to this VG. So we'll do the same thing. We'll do a chart and we'll say that consider what VG will be for a varying ID. And essentially for a diode connected MOSFET, this will be the inverse of the first graph we saw. So you have currents going up to 0, and then it's going to impulse or shoot up to VTH, or the threshold voltage, and then it's going to saturate like this. And if you want to prove this chart, we can go ahead and solve for VG in terms of ID. So what we can say is that ID is equated to 1/2 mu n COX W over L VG minus VTH squared. I forgot to put a squared over here. And then we can go ahead and multiply both sides by 2 over mu n COX W over L. And so we'll notice that the 2's cancel out. The mu n COX cancel out here. And the W over L cancel out here as well. So then we can rewrite this equation. I'm going to write this on the left-hand side as VG minus VTH squared is equated to 2ID over mu n COX W over L. If I go ahead and take the square root of both sides, I'm left with VG minus VTH is equated to the square root of 2ID over mu n COX W over L. As a result, if I add VTH to both sides, VG is equated to the square root of 2ID over mu n COX W over L plus VTH. And essentially here is my second equation. To go ahead and prove this graph here, we can go ahead and put in 0 in for ID. If we plugged in 0, we will just get VTH, which is why at 0 we're at VTH. And then anything for ID above 0, so greater than 0, is VTH plus this entire square root. So I hope this makes sense for the second part of this proof, or this current mirror generated equation. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Okay, so for the last part of this video, what we want to do is attach our beginning circuit with this NMOS, or this transistor connected here, and we want to derive an equation or see what happens. So let's call this I out here. So the first thing we want to note is that VG, so this VG here, is from this node to this node. All right. So this here is VG, and essentially also this here is VG. Long story short, the input to my I out transistor, or my M2 transistor, is VG. So in order to generate a current, we want M2 to be in saturation. So if we say that M2 is in saturation, then we say that I out is equated to 1/2 mu n COX W over L. This is the second transistor, or M2, times VG minus VTH squared. Now we know that VG is this equation here, right? Because we derived this from one of our slides. So let's go ahead and replace it with this VG located here. So then we get that I out is equated to 1/2 mu n COX W over L squared times the square root of 2ID over mu n COX W over L 1, right? Because this VG was derived from my first transistor, M1. And then we're left with a plus VTH. Again, that's still part of this VG, minus VTH, which comes from over here. And then we close that out, and then we square it. We can already see that VTH here cancels out with this one. The square symbol cancels the square root out. So let me write a nice clean equation. So then you can say that I out is equated to 1/2 mu n COX W over L of the second transistor times 2ID over mu n COX W over L of the first transistor. And what we can see is that mu COX here cancels out with this mu COX. This 2 cancels out with this 2. And so I out is essentially equated to W over L of my second transistor over W over L of my first transistor times ID. Now, this ID here is coming from this ID here. And if you remember from the very beginning of the video, we call this our I reference, or the current coming from that golden current source, which we created using a band gap circuit. So essentially, my final solution will tell me that I out is equated to W over L of my second transistor over W over L of my first transistor times I ref. And this here is the final solution. And so just to wrap things up, this here is a very beautiful result because our mirrored current is only dependent on the width and the length of our first MOSFET and our second MOSFET, and independent of temperature and our power supply voltage. As a result, if we wanted to mirror a certain current and keep that current stable on a given component, we can use the current mirror to do this and understand that it will be independent of temperature and our power supply voltage. In the next video, I will be doing 2 examples just to drive home the concept of the current mirror. So please feel free to check that out. If you have any questions or concerns about this concept, please leave them down in the comment section below and I'll be sure to get back to you. If you liked the video, please give it a thumbs up and please share the video to your colleagues and friends. And lastly, if you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.